The tower that shouldn't exist. Imagine walking into a lobby on the coast of the Pacific Ocean. You press a button on a wall panel labeled simply Orbit. You don't put on a spacesuit. You don't undergo months of grueling G-force training. You just sit in a comfortable, climate-controlled cabin with a cup of coffee. Outside the window, the horizon begins to bend. The deep blue of the atmosphere slowly bleeds into the pitch black of deep space. No explosions. No multi-stage rocket drops. Just the quiet, steady hum of an electric motor. 7 days later, you step out onto a luxury hotel orbiting 36,000 kilometers above the Earth. For over a century, we've been trapped by a brutal law of physics, the rocket equation. To lift fuel into space, you need more fuel to carry that fuel. It's why traditional space travel is an incredibly expensive, dangerously volatile exercise in controlled explosions. But what if we could bypass rockets entirely? What if we built a permanent, physical bridge between Earth and the cosmos? Arthur C. Clarke once famously said that humanity would build a space elevator 50 years after everyone stopped laughing. Well, nobody's laughing anymore. Right now, the global space elevator infrastructure market is projected to skyrocket to over $1 billion by 2030, with aerospace titans actively designing foundational anchor platforms. But there's a reason you can't book your ticket just yet. Between our current reality and this sci-fi utopia lies the single greatest engineering nightmare humanity has ever dared to dream up. A project so maddeningly complex that a single mistake wouldn't just waste billions of dollars. It could trigger a global disaster. Tonight, we disassemble the physics, the brutal material limits, and the absolute chaos of trying to build a true space elevator. Part 2. The physics of an upside-down Plumb bob. To understand why building a space elevator is a nightmare, you first have to understand that a space elevator doesn't actually stand up. It hangs down. Think about a classic lasso. If you hold a rope in your hand, it just falls to the floor. But if you spin that rope around your head, the centrifugal force pulls it taut, making it rigid. A space elevator works exactly the same way, but on a planetary scale. At the base, you have an anchor station fixed to the Earth's equator. From there, a continuous cable, called the tether, stretches up past low Earth orbit, past medium Earth orbit, all the way to geostationary equatorial orbit, or GEO, at exactly 35,786 kilometers high. At GEO, an object orbits the Earth at the exact same speed the planet rotates. It hangs perfectly stationary in the sky. If you run the cable out past GEO and attach a massive counterweight, like a captured asteroid or a decommissioned space station, the centrifugal force pulling outward matches the gravitational force pulling inward. The entire structure becomes an upside-down Plumb bob, held perfectly under tension by the literal spin of our planet. But this creates a terrifying structural paradox. Unlike a normal skyscraper, which needs to be thickest at the bottom to support the weight above it, a space elevator cable has to support its own hanging weight. That means it must be thickest at geostationary orbit, where tension is maximized, and taper down to its thinnest point, right at the ocean surface. The math behind this is unforgiving. If you tried to build this cable out of the strongest high-grade structural steel we possess today, the cable would have to be so ridiculously thick at the top to support its own weight that it would require more mass than exists in the entire observable universe. Clearly, steel isn't going to cut it. We need a miracle material.
Part 3. The materials crisis, the 1-meter limit. To survive the immense tug-of-war between Earth and deep space, the tether material needs a specific tensile strength of at least 50 to 130 gigapascals. To put that into perspective, structural steel breaks at around 0.5 gigapascals. We need something roughly 200 times stronger than steel, yet lighter than aluminum. For decades, this was the ultimate dead end. Then came carbon nanotubes, or CNTs. CNTs are tubes of carbon atoms arranged in a perfect hexagonal lattice. On paper, they are the holy grail. Their theoretical tensile strength tops out near 150 gigapascal. When they were discovered, the scientific community collectively gasped. Organizations like Japan's Obayashi Corporation boldly announced blueprints to build a functional space elevator by 2050 using CNT technology. But here is where the nightmare reality slaps us across the face. There is a massive, seemingly insurmountable gulf between theoretical physics and applied engineering. When you synthesize carbon nanotubes in a lab, they are microscopically flawless. But as soon as you try to weave them into macro-scale threads, defects creep into the atomic lattice. A single displaced carbon atom reduces the material's practical strength by up to 70%, dropping it down to an unusable 45 gigapascals. Worse still, nobody has ever managed to grow a perfectly flawless, continuous carbon nanotube strand longer than about half a meter. Let that sink in. To build a space elevator, we need a flawless ribbon that is 100,000 kilometers long. We are currently stuck at less than a meter. The massive tech incubator Google X actually put their space elevator R&D project into a deep freeze for this exact reason. The material simply does not exist yet. However, as we push through the late 2020s, materials science is fighting back. Researchers are now shifting focus away from carbon nanotubes and looking at macro-scale single-crystal graphene and boron nitride hybrids. Quantum computing and advanced AI modeling are being deployed to simulate molecular bonding, attempting to stitch together shorter graphene sheets using fractal patterns that mimic the natural toughness of spider silk. But even if our AI models solve the material crisis tomorrow, and we somehow manufacture a 100,000-kilometer ribbon of flawless graphene, our nightmares are just getting started. Part 4. The environmental meat grinder. The vacuum of space looks peaceful from a distance. Up close, it's a hypervelocity shooting gallery. Right now, Earth is surrounded by millions of pieces of space debris, decommissioned satellites, spent rocket stages, and flecks of paint, all orbiting the planet at speeds exceeding 28,000 kilometers per hour. At that velocity, a stray bolt has the kinetic energy of a hand grenade. A space elevator tether is a stationary, unyielding line cutting directly through this chaotic orbital highway. It cannot dodge, it cannot duck. To survive this, engineers can't use a round cable. Instead, current designs call for a paper-thin curved ribbon several meters wide. If a piece of micrometeorite or space junk punches through it, it only leaves a tiny hole, leaving the rest of the ribbon's width intact to carry the load until a robotic climber can crawl up and patch the wound. But space junk isn't the only thing trying to destroy our multi-billion-dollar elevator. The middle section of the elevator must sit permanently within the Van Allen radiation belts. This area is packed with highly energetic electrons and protons that will relentlessly bombard the tether, degrading its molecular bonds over time. And let's bring it back down to Earth. What happens in the atmosphere? The lower sections of the elevator will be subjected to Category 5 hurricanes, typhoons, and relentless jet stream winds pushing against the cable like a massive sail. If the base is anchored to solid land, these atmospheric forces will bend, twist, and eventually snap the tether. This is why modern engineering consensus rejects a land-based anchor. Instead, the elevator must be anchored to a massive mobile floating ocean platform, very similar to an ultra-advanced oil rig. By using massive thrusters, this floating base station can actively move across the ocean, dynamically shifting its position to literally dodge incoming hurricanes or pull the cable out of the predicted path of trackable space debris. Think about the sheer scale of that choreography. Moving a floating city in the ocean to swing a 100,000-kilometer string out of the way of a supersonic piece of space trash. Part 5. The Climber and the Whisper of Catastrophe. Let's assume we built it. The ribbon is anchored, the counterweight is balanced, and the weather is clear. How do we actually use it? We use vehicles called climbers. These are essentially mechanical locomotives that grip the ribbon and roll their way up into orbit. But unlike an electric train on Earth, a climber can't carry heavy batteries, and it certainly can't drag a power cord 20,000 miles into the sky. So, how do you power a train to space? You shoot it with lasers. Gigawatt-class laser arrays stationed on the ocean platform will track the climber as it ascends, beaming raw energy directly onto photovoltaic panels on the bottom of the vehicle to power its electric motors. But even with flawless laser tracking, these climbers will be slow. Traveling at a conservative 200 kilometers, it will take a climber roughly a week to reach geostationary orbit. And that long, slow journey introduces our final, most terrifying engineering nightmare, the whiplash effect, known scientifically as Coriolis forces. As a climber moves further away from the Earth, it is moving into zones that require a higher tangential velocity to keep up with the Earth's rotation. In plain English, the climber acts as a brake on the planet's spin. As it ascends, it drags the cable backward, causing the entire 100,000-kilometer structure to bow and oscillate. If you send up a climber that is too heavy, or if you send up multiple climbers at the wrong intervals, these oscillations will amplify. The cable will begin to whip wildly back and forth across space. If those waves build up unchecked, the cable snaps. If the space elevator snaps near the top, the lower section, tens of thousands of kilometers of hyper-strong, razor-sharp ribbon, will fall back to Earth. Due to the planet's rotation, it wouldn't just drop straight down. It would wrap itself around the equator like a falling whip, cutting through anything in its path before burning up or crashing into the ocean. The upper section, along with the counterweight, would be flung violently out into deep space, lost forever. The margin for error is exactly 0. Part 6. The ultimate question. The space elevator is an engineering nightmare of epic proportions. It requires materials we can barely synthesize, power delivery systems we are just beginning to test, and a level of structural monitoring that pushes human capability to its absolute limit. But if we conquer it, the rewards will rewrite the future of our species. The cost to launch payloads into space would plummet from thousands of dollars per kilogram to just a few dollars. Space colonization, asteroid mining, and deep space exploration would become trivial overnight. We would no longer be a planet-bound species looking up at the stars. We would be a spacefaring civilization with a permanent front door to the universe. So we leave the ultimate question to you. Is the space elevator a beautiful, mathematically perfect dream that humanity is destined to build? Or is it an inherently unstable structural nightmare that will always remain firmly in the realm of science fiction? Let us know your thoughts in the comments below. Do you think we'll see a working prototype in our lifetimes, or should we keep betting on reusable rockets? If this deep dive into the nightmares of engineering fascinated you, make sure to hit that like button and subscribe. It tells the algorithm that deep human-driven science content matters. Thank you for watching, and we'll see you on the next descent.